Hello, everyone. I'm going to go through a talk today that I gave at the Accelerate conference a few weeks ago, which was hosted by the Acceleration Consortium. I have a lot of nice things to say about them, but to keep it brief, what's great about the Acceleration Consortium, in my view, is that they're not only a group of very clever people, but they're focused on raising the entire community around them, ensuring that the techniques that they create or the software or the data are accessible by the community at large. They even have an education director so that it's not just research that's done by one team that advances a few sets of problems, but it's a consortium that helps raise everybody else around them. So in short, it very well agrees with the way I like to do science or what I aspire towards. So I was very delighted to be part of that conference. Now, the talk that I gave at that conference focused on kind of some aspects of how AI has changed the way that I approach computational problems, taking the lens of how things have changed since I was a graduate student, starting about 10 years ago. It was a 12-minute long talk, so in that spirit, let's get started. So the one thing that I've really learned over the course of doing computational science for only a decade is that already a lot of the things that I have learned or the ways that problems have been approached are now outdated. And we're going to go through them, or at least two of these major improvements to computational science that are due to AI. Why I came to the conclusion that these are bad ideas, and how my team and I are trying to help advance science such that these sort of concepts are no longer pitfalls that other people run into. And the first of which was very well in tune with many ideas in the conference, that instead of the dictum of when in doubt, just run as many computations as you can, instead to focus on letting AI help make the decisions on how you should spend the precious resources that you do have. And this was something that the idea of being able to run large numbers of computations as the way of solving many problems was already something that was, one, very prevalent when I did my candidacy exam about 10 years ago, but was already one that were starting to become rare while I was even already a student. And this here is an example from my qualification exam, showing some recent work from one of my colleagues, with his permission, where we had performed around 200,000 calculations of a particular crystal structure, and around half of them were so unstable that there's no way they would be accessible experimentally. And that's a waste of computing resources, and that's important to consider, because if our cluster was powered on a grid that was entirely coal, each one of these points would be about a pound of coal. So really, just from not only a goal of finishing your science as quickly as possible, but from a notion of resource considerations, these kind of techniques are very expensive. And as we'll soon demonstrate, and you might have seen in many of the other talks from Accelerate, the way around this with AI is a tool known as active learning. You might know it as a few other names: Bayesian optimization, optimal experimental design, but the general idea is that you can use a machine learning model to infer the outcomes of those hundreds of thousands of simulations and use that to selectively pick the best ones. Now, the aspect of this problem that my group has been studying is not just taking these active learning algorithms and deploying them onto HPC, but figuring out HPC, high performance computing, but figuring out how to do so in the most effective manner. Because if we take a look at kind of where these conventional practice lies in terms of how do we do this better, it's not in being able to invent better physics codes. There are dozens available that can solve many types of scientific problems. It's not in the workflow tools to drive them, nor is it in the problem in being able to model these different physics codes and create a simulator for them using AI. Instead, the area that we've been digging into is this interface between the physics and the AI, the so-called concept around intelligent workflows, where we make that AI an embedded part of the normal scientific process. And this is something that many other folks are also exploring. And the particular aspect of the problem that we've dived into is how we can create software that allows us very intricate policies for being able to integrate AI and simulation on HPC. You may have seen this in a few of the other talks that I've posted. It's been something that I've worked on for a long time. But the idea that we're emphasizing here is that there's not one simple policy when I start to employ these active learning on supercomputers that will work very well. If your problem has a large number of tasks, but they all take almost exactly the same amount of time, a batch strategy may work well. You won't run into these underutilization problems that we illustrate on the left when a batch has a number of tasks and some of them take a very long time to complete. In the other case, if you do have a large amount of variance in time, you may want to create a task queue such that you keep up to date asynchronously, such that you always have a task ready to compute regardless of whether a batch has finished or not. And that way you can achieve great utilization at the cost of making each of these individual decisions with less overall data. So what we're hopefully illustrating here is there's not one magic bullet or single policy that one would use for every scientific application, but there's a lot of variance that one should want to explore in order to optimize particular problems. To that end, we've created a tool called Colmena that allows you to express complex policies as a series of simple agents. Now, here is the one particular tool that we created for molecular design. And we decompose the active learning loop into 6 agents, each of them with a relatively simple task. This QC scorer is responsible for pulling the next molecule to be run off a queue and deploying it on the supercomputer whenever resources are available. This is what keeps our utilization high. At the very other end, we have a machine learning recorder that takes inference tasks, and as they complete, uses that information to update the priority in which we run a molecule. Say if we've now learned that, given the latest copy of the data, a new molecule would not be very effective, we deprioritize it. Just as an example of the kind of logic. And you can see here that this submitting a simulation is tied to this eventual machine learning recorder by a series of intermediate steps, each of which are relatively simple in their description, but in combined allow you to create this complex policy for being able to dictate how your supercomputer optimizes what it's doing. In this particular case, let me skip to the next slide. We created a policy using these same recipes of 6 agents that changes state of what it's doing as different types of data come in. For example, at the beginning, I dedicate my entire supercomputer to running inference, and you can see that in that the color is red. You can also see, because the shade isn't completely dark, that only 400 of these nodes at max are actually doing work instead of all 1,000. But that's a transient problem, and I can dig in the reasons behind it. You can also see that after this inference finishes, we then dedicate all nodes to gathering as much data as possible, and over time we switch between using that data to update a model, using the updated model to update our priority list, and continue that on for 6 or so hours. And what we found is at the end of 6 hours, this policy where I continually switch what the supercomputer is doing outperforms a strategy where I do use a machine learning model, but I don't update it by about 10% in terms of the total numbers of molecules it finds. And of course, both of these machine learning oriented strategies outperform a random search by at least a factor of 100. So in short, there's a real benefit here towards combining AI and simulation together into one single app or application. And the way that we've kind of viewed this in the long term is it's moving us away from the notion that simulation can be performed completely disjointed from optimization by employing these high throughput brute force searches, moving gradually towards these hybrid AI plus simulation applications where we ensure that that AI works as harmoniously with simulation as possible. So beyond that particular challenge, one of the other things that has changed in my thinking over time is that machine learning or empirical models in general in science should be treated as ever evolving rather than static. And this is illustrated well by a paper that I read a lot during my master's degree. This here is an interatomic potential that was developed in 2004. And you can see that towards one of the later pages in the paper, after they introduce how they created these models, has a table of all of the model parameters. Now, there are good reasons for recording the parameters in the archival literature. It ensures that reproducibility is effective. But we have gathered more data about cobalt and iron since 2004. So, in theory, we could have made a better model in the past 20 years, given the same technique, the same model form, but by just training it using more information. And this here really kind of motivates one thing that my team has been studying is how can we envision performing or using these empirical models in science if we know that they can change at any moment. And there are a few problems to that. The first of which is that if we imagine using the same kind of simulation algorithm that we've used before, but replace it in some cases with a subroutine that's adjustable, that we've got some questions around whether we can be certain of whether using that subroutine, learnable subroutine, is a good idea, learnable and evolving. There are also some questions around how we create adaptive algorithms that are based around and really leverage the idea that we have an empirical model as part of this overall program and it's going to change over time. Now, some of the problems for this are that, one, stitching these types of algorithms together is complicated software development. I've talked a little bit about Colmena already and how we solve some of those orchestration problems. But there are a few more that have to be considered before we can unlock this future of AI embedded into science applications and that AI model constantly evolving. The first of which is we need to have some sort of guardrails around that model to ensure that it's working properly. And a second, that we need to maintain the same degree of reproducibility that we could trust earlier. How do we keep track of these versions of models? Now, there are more, but I picked these problems 2 and 3 in particular because this has been something that my colleagues and I have been working on. For this first problem, ensuring that surrogate models can be trusted, my former student Yuli Zamora, now at Intel, developed a technique where we embedded a controller within this hybrid application that, as we use the surrogate model, would audit it to see how well it was actually performing compared to what we were replacing, which in our particular case was a density functional theory calculation. And over time, it would adjust the performance of the software by controlling a few parameters like what is the error tolerance that we, or the uncertainty tolerance that we allow for using the model, such that it would maintain a target error level, yet use the surrogate method as much as possible. And the figure on the bottom right is showing that indeed our controller method ensures that we achieve a desired error bound. Our use of the machine learning model is never worse than a certain amount, or is never off by larger than a certain target number, and it does this in a way that maximizes the speed up over simpler strategies for integrating the surrogate. So here it's a very in-depth technique, but hopefully illustrates that there are a lot of open challenges in the field of demonstrating how we combine adaptable AI with conventional simulation codes. Another problem is that sharing the models is something that we don't have much in the way of publication structure for. Sharing the model parameters via papers is good. Sharing them via CSV is better. Sharing them via a GitHub is even more effective at allowing for models to change over time. But what I really want in my software is the ability to call the latest version of a model and let someone else figure out how to actually run it. And that's been the goal behind the Garden project that I've been working with a team out of the University of Chicago, Wisconsin, MIT, and a few others to create a publication platform where someone can share a machine learning model in such a way that others can run it in the cloud, and that this machine learning model can be treated as any other type of publication artifact. We can associate it with authors, we can tie it to the other artifacts that were user created, like data sets or the papers which describe it. And in this way, we can build sort of a next generation of a publication environment that will really make building these integrated models possible. And that's the Garden project, which we have the link down there. So in short, the way that our team has been moving is to address this previous notion that empirical models must be kept static, and building the algorithms which allow us to work with a model that is not only uncertain, but that how its performance is judged is going to change as it evolves over time, with both clever algorithms and the publication structure that can back it. So that's overall my talk today. We've covered kind of two ways of thinking that about computational science that, at least for me, have changed since I was a graduate student in the early 2010s, where one is the idea that instead of approaching problems with as much computational power as we can to run as many simulations as possible, we should really be focusing on how we link AI into the loop, such that we can make these AI tools more efficient by using AI to identify really where that computational resources are needed most. And the second is that we should write these applications in a way that allows those AI components to change. We need some sort of controller to be able to alleviate the human from being able to audit and ensure that the machine learning components are behaving correctly. Our solution was to study a controller instead. And we need publication environments that allow us to share models and evolve them over time in a way that maintains the same degree of provenance and reproducibility that science has become to expect. So that wraps up my talk for today. I have many people who I've been really happy to be working with on these number of problems, and of course that the work wouldn't have taken place without each of their unique insights. At this point, that wraps up the conversation for today. Happy to answer any questions via email or the YouTube comments, and hope you found this helpful. Have a nice day.